Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it.
This is chapter 3.5, which is on exponential and logarithmic models. All right. So let's talk about first the exponential growth model. Now, graphically speaking, it is given by the following function. Y is equal to ae to the bx, where b is greater than 0. Also here, a would be greater than 0. And we end up with the following graph. It looks something like this, all right, where it crosses at the point 0, comma a. All right, that's exponential growth. We also have something called exponential decay. In here, the model is very similar. It's still an exponential model. It's ae to the bx. In here, though, the difference is that b is less than 0. A is still greater than 0, though. All right. And with exponential decay, what we end up with is the following. We end up with a graph that looks like this, also crossing at the point 0a. All right. So that's exponential growth and exponential decay. Let's look at something called the Gaussian model. Now, the Gaussian model is given by the following function. Y is equal to e to the negative of, let's rewrite that. Y is equal to ae to the negative x minus b squared over c. All right, now in here, this is called a bell curve. You would see this kind of graph in a statistics course. So I'm not going to focus on this graph too much, but that's essentially what the bell curve looks like. All right. Another that's exponential or logarithmic. Let's look at logistic growth. All right. And logistic growth is similar to a logarithmic function, sort of. It looks like this. It's y is equal to a over 1 plus be to the negative rx. All right. Now, in here, this graph looks like this. We're gonna have two horizontal asymptotes. All right, and it looks essentially something along the lines of this. All right. So that's logistic growth. It's somewhere between a logarithmic and an exponential as far as the growth itself. Let's look at number 5. The fifth model here that we'll discuss a little bit is, well, the actual logarithmic models. And the logarithmic model, it would follow functions like this. Y is equal to a plus b log base c of x. If we do this with ln, it would be a plus b ln of x. If we do it with the common log, it would be a plus b log of x. All right. But either way, they all look essentially the same. Where it looks something like that. All right. Having this vertical asymptote of the y-axis. All right, so let's see some examples of some of these. So first, let's discuss growth, so population growth. And let's write in white. So here's an example. The number of bacteria in a culture is increasing according to the law of exponential growth. Right. After 1 hour, 100 bacteria. Hold on, let me rephrase that. After 1 hour, there are 100 bacteria. After 2 hours, there are 200 bacteria. All right. Let's say, and after 2 hours, there are 200 bacteria. Here. How many bacteria will there be after 3 hours? All right. So again, I'll read this real quick. It says the number of bacteria in a culture is increasing according to the law of exponential growth. After 1 hour, there are 100 bacteria, and after 2 hours, there are 200 bacteria. How many bacteria will there be after 3 hours? So in here, well, we're told something very explicitly here. We're told that we're doing exponential growth. So right away, we know that we're working with the function of y equals ae to the bx. All right, so we already know that. Now, we want to come up with this function so that we can figure out what happens after 3 hours, all right? And what we're going to do here is, well, we're also given some other information. We're told that after 1 hour, there's 100 bacteria, and after 2 hours, there are 200 bacteria. So essentially, we could think of this as the points 1, 100, and the point 2, 200. Right, so we could think of those happening there, where the first column represents the time, and the second column represents the number of bacteria. All right, or I should say the first component and the second component. Now, well, what does this do for us? Well, from the very first point here, we can say that this tells us that when I plug in 1, I'm supposed to get 100 into this setup. So let's see how that works. So my y value would be 100. It's going to be ae to the b times 1, which just simply simplifies to just be 100 is equal to ae to the b. We still don't know much about a or b. All right. Now, in this one right here, let's apply the same idea. If I plug in 200 for y and 2 for x, I end up with 200 is equal to ae to the b times 2, which tells us that 200 is equal to ae to the 2b. Now, here we have 2 equations, 2 unknowns. We can try to solve this, all right? So essentially what we're going to do here is, in each of them, we're going to solve for a. So from here, we know that a is equal to 100 over e to the b. And from here, we know that a is equal to 200 over e to the 2b. They're both the same a though, all right? They're just being applied with a different x value and y value, but they come from the same function, so they must be the same a. So what we're going to do now is we're going to set these equal to each other, and we're going to say, well, 100 over e to the b is equal to 200 over e to the 2b. At that point, we're going to say, well, we can do some cross multiplication, and I end up with e to the 2b over e to the b is equal to 200 over 100. In other words, e to the b is equal to 2, right? All I did was apply the rules of exponents here and reduce, which tells me now that b is equal to ln of 2 by just taking the ln of both sides. So now I've got the value of b, which is great because that tells me I can figure out the value of a. And it doesn't matter which of these two I plug it into, all right? I'm still going to be able to get the value of a. I'm going to plug it into the first one though. So this tells me now that a is equal to, we had 100 over e to the b, and here b is going to be ln of 2, which gives us 100 over 2, meaning 50. Right in here, the e and the ln cancel each other out. So a is 50, b is ln of 2. So what this tells us now is that y is equal to, remember the exponential model was ae to the bx, right? It was ae to the bx. But in this case, we're going to say, well, a was 50. E, well, we still have the e there. But b was ln of 2, and then that times x, right? Now, from rules of exponents here, well, we can put these parentheses here, and that tells us that what we really have is just 50 times 2 to the x, right? Because e and the ln cancel each other out. So that's our model. Our model is y is equal to 50 times 2 to the x. So, why do we care about that? Well, now that we've got the model, we can figure out exactly what's happening after 3 hours. Remember, our x values were time. So, what happens after 3 hours? Well, we're going to say, well, this implies now that y is equal to 50 times 2 to the third, which is 50 times 8, right? 2 to the third is 8. And then 50 times 8, well, 5 times 8 is 40, but we have another 0, so 400. So after 3 hours, there's going to be 400 bacteria. All right? And again, it's because we were doing exponential growth. If this had been linear growth, you might have been inclined to think, or you would have been correct, if this were linear growth, you would have said, well, after 3 hours, it would be 300 bacteria, because it's just adding by 100 each time. That's assuming it was linear growth. But in here, we've got exponential growth. So essentially what's happening is it's doubling after every hour. So after 1 hour, after 1 hour, we had 100. After 2 hours, it doubled to 200. So this actually also tells us something, all right? We can figure out how many bacteria we started with, all right? And if we wanted to do that, we would just plug in 0 into here. So perhaps I'll do that as a side comment. How many bacteria did the experiment start with? And we're going to say, well, when you start an experiment or anything like that, that time would be equal to 0. In other words, in this case, the x value is equal to 0. So what would happen there, we would have y is equal to 50 times a to the, well, no, hold on. 50 times 2 to the 0. 2 to the 0 is 1. So 50 times 1 is just 50. So we started with 50 bacteria. All right. And you'll notice that will definitely follow the pattern, right? Because if you start with 50 bacteria, after 1 hour, it doubles, 100 bacteria. After another hour, it doubles again. So from 100 to 200. After another hour, it doubles again. We found out that after 3 hours, it became 400 bacteria. So after 4 hours, you would expect that it would be 800 bacteria, so on and so forth. All right, so that's exponential growth. Now, let's talk about exponential decay. All right, but the example we talk about is with carbon dating. All right, so carbon dating is exponential decay. So let's do the example. Example B. To estimate the age of that organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time t. And t here would be in years. And this is the model, or the formula. The ratio is equal to 1 over 10 to the 12 times e to the negative t over 8,223. All right. In here, this 8,223 essentially talks about the half-life of carbon-12. Now, estimate the age of a newly discovered fossil for which the ratio of carbon-14 to carbon-12 is R is equal to 1 over 10 to the 14th. All right, so in here, we're given a formula, and we're told that this formula really denotes the ratio of carbon-14 to carbon-12, right? We're told what the ratio is. So all we need to do here is set these two equal to each other. So I'm going to say here that 1 over 10 to the 14th is equal to 1 over 10 to the 12 times e to the negative t over 8,223. And what we're going to do there is we're going to solve for t. T here will be time because we're looking for the age of this fossil, right? So let's solve for t. Well, what are we going to do? I'm going to multiply this 10 to the 12th up here. So I have, well, 10 to the 12th over 10 to the 14th is equal to e to the negative t over 8,223. But 10 to the 12 over 10 to the 14th is really 1 over 100. And we have this equal to e to the negative t over 8,223. Taking ln of both sides, I end up with ln of 1/100 is equal to negative t over 8,223. And lastly, I'm going to multiply both sides by negative 8,223, which gives me that t is equal to negative 8,223 times ln of 1/100. All right. Now, from rules of exponents, from rules of logs, we can say, using the power rule, well, we end up with 100 to the negative 1, which equals here, bring this negative 1 to the front, 8,223 times ln of 100. Now, plugging in this into the calculator, you would end up with a value of approximately 37,868. And this is in years, right? The only part that we did in the calculator was this last part over here, plugging that in. But again, it's just a matter of setting up your exponential equation and solving for the variable. So that was exponential decay. Let's talk about another common exponential growth problem, which is with interest. So example C. How long would it take to double an investment if it is continuously compounded at an annual interest rate of 6.75%, right? And this is if. The second question is going to be, how long would it take to triple? All right. So I'll read the question again. It says, how long would it take to double an investment if it is continuously compounded at an annual interest rate of 6.75%? How long would it take to triple it? All right, so first let's look at the doubling. All right. And let's see what we know about here. We know that it is continuously compounded, right? It is continuously compounded, and it's got an interest rate of 6.75%. So what does that really tell us? Well, because it's continuously compounded, we know we're looking at A equals PE to the RT. And notice that that's essentially exponential growth. Y equals AE to the BX, right? It follows the same exact pattern or the same exact format. So that's how we know what formula we're going to be working with, the continuously compounded formula. And what do we know? We have the interest rate of 6.75%, which means we're working with a decimal of 0.0675, right? Those are the two things we know. Now, let's read in between the lines. What does this actually want us to do? It wants us to double the investment. Well, what does that mean? Well, what that says is that whatever you start with, you want to double it, right? What you start with is called the principal, right? What you end with is called the amount, as far as this formula goes. So what this is telling us now, because we want to double it, this is telling us that this formula is going to be 2a is equal to, excuse me, let me rephrase that, that's bad. 2p is equal to PE to the RT, because whatever you start with, P, your principal, you want to double it. Your final amount, you want to be double what you start with. And from there, well, this really tells me now that 2 is equal to E to the RT. We know what R is. So if I plug in R, I end up with 2 is equal to E to the 0.0675 T. Taking ln of both sides, I got to ln of 2 is equal to 0.0675 T. Dividing both sides by 0.0675, I get that T is equal to ln of 2 over 0.0675. And plugging that into the calculator, you would get a value that is something like 10.2688. So you can say essentially approximately 10.27 years, because remember in this formula, time is in years. So that's for doubling our investment. That's the first question. Let's look at the second question. How long would it take to triple it? Well, let's think about that. So tripling it. We're going to start with the same information, right? We still have this formula of A equals PE to the RT. The interest rate is still the same. What changes here, however, is the amount that we want to end up with, because we want to triple it. So because we want to triple it, that tells us now that the amount that we want to end up with is 3 times the principal. Because remember, P, the principal, is what we start with. Well, from here, dividing both sides by P, this tells me that I really have 3 is equal to e to the RT. And now, once I have this, I know what my interest rate is. So continuing this, I take ln of, well, actually, let's plug in the value of R. So e to 0.0675 t. At that point, we take the ln of both sides. So I end up with ln of 3 is equal to 0.0675 t, which tells us that t is just simply ln of 3 over 0.675. Plug this into the calculator, you get something like 16.2757, which we're going to round to be 16.27 years. So let's look at that. Let's look at the information we got here. To double it, it took us an entire decade, a little bit more than a decade. But to triple it, it didn't take us a whole extra decade after that. All right. It is exponential growth. So that's how you know that it's going to take exponentially longer. Excuse me, exponentially shorter, because it's growing exponentially fast. All right. So that's why it doesn't take a whole extra 10 years to raise the same amount of money. All right. At least through compound interest. All right. Now let's look at logistic growth. So logistic growth. All right, and just to remind you, that was when we had y is equal to a over 1 plus be to the negative rx, right? And the graph for something like that looks like this. It's got 2 horizontal asymptotes, and essentially looks like this. All right. Now, let's do an example. So, example, I think we're in example D. On a college campus, of 5,000 students, one student returns from vacation with a contagious, oh, that's how you spell contagious. Contagious. I think that's correct. And long-lasting virus, or long-lasting flu virus. The spread of the virus is modeled by, and here's our model. Y is equal to 5,000 over 1 plus 4999 e to the negative 0.8 t. All right, where t here is greater than or equal to 0. T represents the time. Y here represents the total number of students who have been infected by this flu-like virus, or this flu virus. All right. Now, the college will cancel classes when 40% or more are infected. So the first question is, how many students are infected after 5 days. The second question, after how many days are 250 students infected? And the third question is, after how many days will the college cancel classes? All right, so I'll read it again. It says, on the college campus of 5,000 students, one student returns from vacation with a contagious, long-lasting flu virus. The spread of the virus is modeled by y equals to 5,000 over 1 plus 4,999 e to the negative 0.8 t. Here, t represents time in days. So let's see, time in days. And y represents the number of people infected, the number of students infected. So, all right. The first question, how many students are infected after 5 days? Well, the first question is easy. This is our solution. So the first question is, well, we know this is our model. We're asked about 5 days. Well, that's our time in days. T is our time in days. So let's go ahead and plug that in. So we have y is equal to 5,000 over 1 plus 4,999 e to the negative 0.0, excuse me, e to the negative 0.8 t. And well, this is just really plugging in that 5 there. So instead of t, I'm going to say 5. Plugging this into the calculator, we end up with 54 students. All right. It's not exactly a 54 value. It's 54 and change, 54 point something. But since we're talking about people, we're going to say that totals 54 students. Second question. The second question was, after how many days are 250 students infected? Well, let's see. Y represented the total number of students, right? So we have total number of students infected. So we're going to plug in that 250 for our Y. Now we end up with 5,000 over 1 plus 49999. I think I said too many nines. 0.8t. There we go. So now in here, I'm going to do some little trickery with the arithmetic to solve this problem. First, realize that this is 250 over 1. And what I'm going to do here is, if I have A over B is equal to C over D, what I can essentially do is multiply by D over A, and this gives me the following equation. On the left side, D over A times A over B just becomes D over B. On the right side, C over D times D over A becomes C over A. So from that, it follows then, this is A, B, C, and D. It would follow that 1 plus 4,999 e to the negative 0.8 t is equal to 5,000 over 250. All right. And well, 5,000 over 250, well, that's just equal to 20. So I have 1 plus 4,999 e to the negative 0.8 t is equal to 20. Subtract both sides by 1. 4,999 e to the negative 0.8 t is equal to 19. Divide by 4,999. I end up with 19 over 4,999. From there, take a ln of both sides. I end up with negative 0.8 t is equal to ln of 19 over 4,999. Divide both sides by negative 0.8. So I end up with t is equal to ln of 19 over 4,999 over negative 0.8. Plugging that into the calculator, you get that will be approximately 6.9 days. So essentially a week. So based on this model for this for the way that this virus spreads, we would have that even though we started with 1 student, after, well, we already know that after 5 days we had 54 students get sick. But we just found out that it would take about 7 days for 250 people, or 250 students, to get infected. All right. And all right, let's look at the third question. After how many days will the college cancel classes? Well, we already know that it would take 40% of the students being infected for the college to cancel classes. We know, all right, so in here for part 3, not part C. For part 3, we need 40% of 5,000 students to be infected. 40% of 5,000, mathematically speaking, just really means 40 over 100 times 5,000. All right. Now in here, I can say, well, this 100 cancels out 100 of those, and we just say, well, 4 times 5 is 20, and then we have 2 zeros to worry about, so 2,000. So 40% of 5,000 is 2,000. So the question really here is, for part 3, is how many days will it take for 2,000 students to get infected? Because that's when the class, well, I mean, that's when the college will cancel classes. So we're going to do the same exact thing that we did on part 2, but we're going to do it with 2,000 people being infected. So we got 2,000 is equal to 5,000 over 1 plus 4,999 e to the negative 0.8 t. Applying the same exact trick from before, I'm going to say that I have 1 plus 4,999 e to the negative 0.8 t is equal to 5,000 over 2,000. All right. Now 5,000 over 2,000 is just 5 halves, right? Because they're both divisible by 1,000. So I have really here 1 plus 4,999 e to the negative 0.8 t is equal to 5 halves. Subtract 1 from both sides. 2,999 e to the negative 0.8 t is equal to, well, 5 halves minus 1 is 3 halves. All right. Divide both sides by 4,999. So I end up with e to the negative 0.8 t is equal to 5 over 2 times 4,999. Taking ln of both sides, I end up with negative 0.8 t is equal to ln of 5 over, well, 2 times 4,999 is 9,998. All right. And finally here, we divide both sides by negative 0.8, and I get t is equal to ln of 5 over 9,998 over negative 0.8, and this would be approximately 10.14 days. And from here to that last step, that's a calculator issue, right? Just plug it into the calculator as that. So after 10.14 days, we ended up with 2,000 people being infected. This example here shows essentially how epidemics spread. All right, you start here with 1 person being infected, right? And in here we have a closed environment of 5,000 students. But in here we have 1 person comes back being infected. After 5 days, 54 students were infected. After, well, in part 2, we saw that it took only 7 days to get 250 students infected. That was just an extra 2 days from when we only had 54 students. So in an extra 2 days, we had an extra 200 people infected for a total of 250. Now here, it took us, in example 3, it took us just another 3 more days to get to a total of 2,000 people being infected. All right. This right here shows how, or this kind of model is super common for epidemiologists, right? All right. There are other kinds of models that exist that are similar to exponential or logarithmic models, but these are the only models that I would like to talk about. So this is the end of 3.5.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.